The James Webb Space Telescope has given scientists a new look at this ancient period of cosmic history, and what it has revealed is forcing researchers to rethink how quickly black holes could form and grow. The question is simple, but the answer is anything but simple. How did black holes become so massive when the universe itself had barely begun? To understand the mystery, we first need to understand how black holes normally grow. Many black holes begin their lives when massive stars reach the end of their lives. After exhausting their nuclear fuel, the core of a massive star can collapse under its own gravity. Under the right conditions, that collapse can create a black hole. But these black holes start relatively small compared with the supermassive black holes found at the centers of galaxies. To become enormous, they need to gain mass. They can do that by pulling in gas and dust from their surroundings. They can also grow when black holes merge with one another. The problem is that both processes take time. A young black hole needs enough material around it, and it needs an efficient way to consume that material. Mergers also require black holes to come close enough for gravity to bring them together. That becomes a major problem when we look at the early universe. Some of the black holes detected by Webb existed only a few 100 million years after the Big Bang. That may sound like a long time to us, but on the scale of cosmic history, it is incredibly short. The universe had barely begun its journey, yet some black holes were already approaching enormous masses. One reason Webb is so important is that it allows astronomers to look deep into cosmic history. When we observe an extremely distant galaxy, we are not seeing it exactly as it exists today. We are seeing ancient light that left that galaxy billions of years ago. The farther away the object is, the farther back in time we can see. So when Webb observes a galaxy from the early universe, astronomers are essentially looking at a snapshot from a period when the first galaxies and black holes were still developing. And that ancient snapshot has revealed something unexpected. Black holes may have been growing much more efficiently than many traditional models predicted. One important example is a black hole known as LID 568. Researchers studying this object found evidence suggesting that it was feeding at an extremely high rate, potentially far above the commonly used Eddington limit. The Eddington limit is connected to a balance between gravity pulling material inward and radiation pushing material outward. As gas falls toward a black hole, it becomes extremely hot and can release enormous amounts of radiation. That radiation can push against additional incoming material. So, under ordinary assumptions, there is a limit to how quickly a black hole can consume surrounding matter. The faster it feeds, the stronger the radiation pressure becomes. This creates a natural restriction on how quickly the black hole can continue growing. For a long time, this idea was an important part of black hole growth models. But objects like LID 568 suggest that the real universe may be capable of producing much more extreme feeding episodes. Researchers do not necessarily think that such a black hole remains at this extreme rate forever. Instead, the intense feeding could be a temporary phase. Even so, a short period of extremely rapid growth could have a major impact on the black hole's overall history. And that brings us to the central mystery. If some black holes were growing extremely quickly, while the universe was still very young, perhaps the problem is not only how fast they grew. Perhaps the bigger question is how massive they were when they were born. This is where the idea of black hole seeds becomes important. Imagine two black holes. The first begins with a mass similar to that expected from the collapse of a massive star. The second begins with thousands of times more mass. Even if both grow at similar rates, the second black hole has an enormous advantage from the beginning. That possibility has led scientists to investigate a process known as direct collapse. Instead of forming from the remains of a single star, A direct collapse black hole could theoretically form from a huge cloud of gas in the early universe. Under very unusual conditions, the cloud might avoid fragmenting into ordinary stars and instead collapse toward a massive black hole seed. Such a seed could potentially begin with thousands of solar masses. That would dramatically reduce the amount of growth needed to eventually produce the enormous black holes seen in the early universe. But direct collapse is not an easy solution. The gas cloud has to remain stable enough to collapse in the right way. If it breaks apart into smaller pieces, those pieces may form stars instead. The chemistry of the gas, the surrounding radiation, and the cloud's rotation could all influence what happens. Computer simulations can produce direct collapse black holes under certain conditions, but scientists are still investigating whether the process could happen frequently enough to explain the growing population of massive early black holes. And then Webb revealed another strange group of objects. Astronomers began finding compact, unusually red sources in the early universe. They became known as little red dots. At first, researchers were unsure what these objects actually were. Were they young galaxies? The mystery does not end with massive black hole seeds. If anything, the discoveries made by the James Webb Space Telescope have opened an even bigger question. What if the early universe had several different ways of building black holes at extraordinary speed? One possibility is that black holes were not growing through gas alone. They may also have been growing through mergers. The early universe was a much more crowded and chaotic place than the cosmos we see around us today. Small galaxies were constantly forming, colliding, and combining. Their central black holes could potentially interact with one another as these galaxies merged. If black holes repeatedly collided and merged, their masses could increase much faster than through ordinary feeding alone. Imagine a black hole gaining mass from gas, then merging with another black hole, then continuing to consume gas inside the newly combined galaxy. If this process happened repeatedly, a relatively small initial seed could potentially become enormous in a surprisingly short amount of time. But there is another challenge. Black hole mergers require the objects to get close enough to interact strongly. Scientists therefore need to determine whether the early universe was dense enough to produce these merger events frequently. Some simulations suggest that environments containing large numbers of young galaxies and black holes could create conditions where mergers became much more important than they are in the modern universe. But again, this is still being investigated. There is no single mechanism that currently explains every observation. And this is where the strange little red dots become especially important. When Webb first began revealing these objects, astronomers were surprised by how common they appeared to be. They were small compared with many modern galaxies, yet their light could be unusually strong and red. For a while, scientists were unsure whether they were seeing normal galaxies or something fundamentally different. One explanation is that powerful activity from an accreting black hole could be responsible for much of the light. If that is correct, then some of the objects that initially looked like unusual young galaxies may actually be systems dominated by growing black holes. This matters because it changes how astronomers estimate the amount of stellar material inside these galaxies. If a black hole contributes a significant amount of the observed light, then interpreting the entire object as starlight can lead to incorrect estimates of its stellar mass. That means some of the apparent tension between black hole mass and galaxy mass could potentially be reduced once the contribution from active black holes is properly understood. But even after accounting for these effects, some early objects remain difficult to explain. And that is why researchers are looking beyond ordinary black hole growth. One of the more unusual ideas involves dark matter. Dark matter is believed to make up a large portion of the matter in the universe, but it does not interact with light in the same way ordinary matter does. We know it primarily through its gravitational influence. It helps hold galaxies together and plays an important role in the formation of large cosmic structures. But scientists still do not know exactly what dark matter is made of. That leaves room for different theoretical possibilities. Some researchers have proposed that a small component of dark matter could behave differently from the standard picture. One such idea involves extremely strong interactions between dark matter particles. If this type of dark matter existed, it could potentially become concentrated in the centers of early galactic structures. Under certain conditions, that concentration might help create unusually massive black hole seeds. The idea is highly theoretical. There is currently no confirmed evidence that this special form of dark matter exists. But scientists investigate such possibilities because the observations are forcing them to consider mechanisms beyond the simplest versions of existing models. And that is exactly how scientific progress often happens. A new observation creates a problem. Researchers test the old explanation. If it does not work, they modify the model. If the modified model still fails, they investigate new possibilities. Eventually, one explanation may survive repeated tests. The same process is happening with early black holes right now. Another important discovery has pushed the problem even further. Astronomers have identified a supermassive black hole from a time when the universe was only around 500 million years old. The black hole already contained hundreds of millions of solar masses. That is an astonishing amount of material for such an early period. The difficulty is not simply that the black hole is massive. It is that it had so little cosmic time available to reach that size. This observation puts pressure on models where black holes begin as relatively small stellar remnants and then grow steadily under normal conditions. There may simply not have been enough time. Unless, of course, something unusual happened. Perhaps the original seed was already enormous. Perhaps the black hole experienced periods of extremely rapid accretion. Perhaps it merged repeatedly with other black holes. Or perhaps several of these processes worked together.